Cumulative distribution functions. A cumulative distribution function, often noted CDF, is another way to consider the information we had when we looked at density functions. The CDF of a density function is defined as the antiderivative from negative infinity up to a point t of the density function, which represents the fraction of a population having values of x below t. So what that means is that we're considering what fraction of the population has a certain characteristic up through value t. So we are accumulating the area from the starting point all the way up to the point t, hence the word cumulative. We know from our earlier work that when we take the antiderivative, that the relationship is that if you want to go back to the original, you would take the derivative of that function. So a cumulative distribution function is the antiderivative of the density function. So we can go back and forth between these two depending on the type of information that we want. Now, some of the properties that a cumulative distribution function has include that the CDF needs to be increasing or non-decreasing. So since we're accumulating area over time, the function should be going up, increasing. Sometimes it levels off because we don't accumulate any area. Therefore, that part is non-decreasing. So it can be constant or it can be increasing, but it can never decrease. Similarly, if we take the limit as t goes to infinity of our CDF, that will have to equal 1 because eventually we will get all of the area under our density function. And remember, the area under a complete density function has to be equal to 1. So a CDF has to eventually get to 100% of accumulating that area. Similarly, if we take the limit as t goes to negative infinity, eventually we'll get past the point where our density function had started and no area will have been accumulated because we'll go past where we started. So if we go in the direction of negative infinity, then that limit has to be 0. Finally, if we integrate our density function between 2 points, a and b, we know that that represents the fraction of the population that has a certain characteristic between a and b. But we also know from the fundamental theorem of calculus that that has to be the antiderivative at the upper bound minus the antiderivative at the lower bound. So we can tie in what we know about antiderivatives into our discussions about density functions to look at our data in another way. So let's do an example using the age function to see how the CDF works. Example 1. Use the age density function below to generate a table for the cumulative distribution function values in increments of 10 years. So here again, we have ages of a certain population given in 10-year spans and the percentage of the population that falls into that age category. So that helps us determine a lot of things. It helps us determine which fraction of the population would be between two ages. We're able to talk about if we pick someone at random, what's the probability that they would be a certain age. But what we want to look at is what percentage of the population falls below a certain age. So that's the type of information that the CDF will tell us. So how does this work? So at t equals 10, so at 10 years of age, the entire cumulative percentage here is 14%. So this is 0.14. So that means if we start at the starting point of 0 and we go all the way until the age of 10, we've accumulated 14% of the population. Now, to talk about the CDF at 20, that means we need to have all of the accumulated percentages from 0 to 20. So we would add up the 14 and 15%, we turn that into a decimal, and we would get 29%. So again, that answers the question, what fraction of the population is less than or equal to 20. So it's everybody all the way up until the particular point. Now we want to keep going. So at 30, we need to add up all the populations from 0 to 30. So if we add those all up, we're going to get 0.43. So 43% of the population is less than or equal to 30. And then we keep going. So to get to 40, we need to add on another 15% here. So that's going to give me 0.58. To get to 50, I have to add on another 15%, which is going to give me 0.73. To get to 60, I have to add on another 11%, so 0.84. To get to 70, I'm going to add on another 7%, so 0.91. To get to 80, I'm going to add on another 6%, so 0.97. To get to 90, add on another 2%, 0.99. And then finally, to get to 100%, and I get to a full 100%. So remember, what that tells me is that 100% of people in this population are 100 years old or less, which we know from before are our bounds, because our PDF, all the area accumulated, has to add up to 1. So when we talk about the cumulative distribution function, we're talking about the fraction of the population having a particular characteristic. So the types of things we might ask, we might say something like P of 60. So P of 60, according to this chart, is 0.84. So what does that tell us? That tells us that 84% of this population is 60 years old or less. So remember, the CDF is going to tell you what percentage are less than or equal to a certain point. And here we're talking about age, so that's why it was 60 years old or less. So we can take the information we have from our density function and represent it in another way by doing the cumulative distribution function. Again, we need our CDF to be increasing or non-decreasing. We can see the numbers here are going up, so that fits with there. And it's got to approach 100%. We can't go above 1 because our entire population is 100%. And we're approaching it because we're increasing from 0 up to 1. So let's look at another example. Example 2. So consider the density function for age distribution, but now given graphically instead of in a table, which means it's a little more approximated than when we had the exact values. Additionally, we have a picture of the CDF below, a fraction of the population as we accumulate people over the span of 0 to 100 years. Notice that we're still considering people from 0 to 100 because that's our age span. Let's start by talking about the density function. So the density function on top is going to show us here that the area accumulated between 0 and t is the antiderivative, or the CDF, up until that point. So again, that's going to tell us how many people have a particular characteristic, which here is age, up until t. So if we looked for capital P of 50, we would be looking for the percentage of people who have an age of 50 or less. And that is all the area accumulated from the starting point up until t. So we have our histogram, and the area under the curve from the starting point until t is what we use for our CDF representation in our picture here. And we know we can get that by integrating our density function. Now, when we graph our CDF, what we're doing is we're graphing the percentage of the population that is less than or equal to a particular age. So as we accumulate area, the amount of people is going up and up and up. We know that CDFs have the property that they should be increasing and that they should be approaching a value of 1. So that's what's happening here. We can see that we are accumulating area and that by the time we get to 100, we've reached 1, which is 100% of the population. So how do we use these graphs to then approximate values? So we want to approximate capital P of 20. Remember, when your P is capitalized, we're talking about the cumulative distribution function, the CDF. If it's lowercase, that's when we're talking about the density function or the probability density function, often referred to as the PDF. So here we have capital P of 20, capital P of 40, and capital P of 80, which means that we're looking for the percentage of the population that is less than 20 years old, less than 40 years old, and less than or equal to 80 years old, respectively. So we're going to look at each of these two pictures, these graphs, and figure out how we can determine this information. Then we can check our answers from the table in example 1, since that gives us more accurate information to make sure that we're doing our process right. So we're going to start by trying to approximate P of 20. So that's the fraction of the population who's 20 years old or less. So first, we're going to start on our cumulative distribution function. And what we want to do to approximate this is we want to see what the level is of our CDF when our age is 20. So we're going to take our 20, we're going to go up until we hit the function, and then we're going to come over here to our vertical axis to figure out what fraction of the population that hits. Because we're accumulating it over time, that means the dependent value is going to give us that fraction of the population. So this appears to be right in between 20% and 40%. So a pretty good approximation here, I would say, is 30% or 0.30. So again, this is just an approximation. So it's a little bit less reliable than having the exact information from the table. But if this is the type of picture we have, if we don't have better information, then this is pretty good. How do we do a similar thing on our density function picture? So the equivalent calculation here is going to be to look for all the area accumulated from 0 to 20 under our density function curve. So what we have to do is we have to look at what these numbers mean. On the vertical axis, we have the percentage of the population per year of age. So since this is a percentage, we need to turn this into a decimal. So this will be 0.015, this will be 0.01, and this will be 0.005. So what I want you to notice here is that we have basically a rectangle and a triangle from 0 to 20. So if I'm approximating the area under the curve, I'm going to approximate the area of the rectangle and the area of that little triangle and add them together. So I notice that this doesn't go all the way up to the 0.015 mark. It's a little bit less than that. So what I'm going to do is I'm going to pick something just a little bit less than 0.015, so 0.014 to be my height. So if I multiply 20 times 0.014, I'm going to get 0.28. And then for my little triangle here, I'm going to do 1/2 base times height. So my base here is 20 units long, and my height, because of the way I picked this, is going to be 0.001. So if I multiply those all together, I get 0.01 for my little triangle here. So adding those together, 0.28 and 0.01, I get 0.29. So that's really close to what I got when I approximated from my cumulative distribution function. So I know that my fraction of the population should be in the neighborhood of 30%. It's really good when those two things are really close because they represent the same thing. So approximations should be within approximately 2% of one another, and we are here. So let's see what happens when we try to approximate the fraction of the population that's less than or equal to 40 years old. So because we're accumulating area as we go, we're expecting this to be a higher fraction of the population because this includes all the people who are 20 or less, and now also includes the people between 20 and 40. So we're expecting a higher fraction than our last calculation. So again, we're going to start with the CDF. We're going to look at the picture on the bottom, and we're going to try to approximate by looking at the value that we get on our function by seeing where we are on the vertical axis. So when I go to 40 and I go up until I hit the vertical axis, that looks like it happens at approximately 60%. So that hits right around 60%, and so I'm guessing that the fraction of the population is going to be roughly 60. So let's see what happens when we go up to our density function and we try to add on that area. So 40 is here. So now we have this sort of goofy shape we have to deal with. So we'll talk about that in a minute. But what I did is I drew another rectangle at 40, and there's a little bit of area above, but I made the height of the rectangle the same as the height of my previous rectangle to make my calculation a little bit easier, because I already know that this area is 0.28 because it's the same calculation as before. Only now I have to figure out how to deal with this area that's on top. That's here. So I'm looking like I want to do a little maybe rectangle here minus a little bit. So if I do a little rectangle here, then the base is 20, the height is 0.1, so that's going to give me 0.02, but it's a little less than that, so I have to make a decision if I want to represent it as 0.01 or 0.02. I think realistically either would be fine, but I'm going to go with 0.02, which again is base times height. My base is 20, my height is 0.001. So if I multiply those together, I'm going to get 0.02. So remember, I have to add up all four areas now, right? So all the areas that I had up until 20, which I know was 0.29, plus another 0.30, that's going to give me 0.59. So again, my approximations are really close, which is great because that's exactly what I want, because again, our two graphs are representing our data, but in different ways. So we should be getting the same approximation. So finally, we want to look at what's happening at 80. So again, we can go ahead and start with our CDF. So at 80, we're going to go all the way up here. And you can see it's just a tiny, tiny, tiny bit below the absolute 1 mark. So here, my approximation for this would probably be 0.99, because I can see that it's almost at the 1, but it's not quite there yet. So it's just a little bit below. So 0.99 or 0.98, I think, is a pretty solid approximation here. Now, on our density function, I want to remind you about something we talked about in the last section, which is complementary fractions here. So I could add up all the area from 0 to 80, right? And that would probably be just fine. I could draw on another triangle and rectangle. But another thing that I can do is I can look at the area from 80 to 100, which looks like roughly a triangle here, and I can subtract that from 1, because I know that the entire area is 100%. So if I'm looking for the area from 0 to 80, that's the same thing as 100% minus the area from 80 to 100. So let's do it that way first, and then we'll go back and do the bigger area. So if I'm looking for this area, I have to do 1/2 base times height. And the base I know is 20 years because it's 80 to 100. But now I have to figure out what the height is. So if I kind of trace this along all the way back here, I see that it's a little bit below the 0.005. So I'm going to go ahead and call this 0.003, partially because I already know the answer to this, but because it's about halfway between 0 and 5, and I'd rather not divide into a smaller fraction. So I think 0.003 is reasonable. So when I multiply these together, I'm going to get 0.03, which means that for my approximation, I'm going to do 1 minus 0.03 to give me 0.97. So again, the reason I'm subtracting this from 1 is because what I'm actually looking for is all of the area from 0 to 80. So I'm subtracting off the area after 80 from 1 to get the area before 80. So this would give me 0.97%, which I think is a pretty good approximation. Now, if I didn't remember that I could do this complementary fraction here, what I could have done is I could have taken the remaining area and kind of divided it up into a rectangle and a very, very rough triangle here. Very rough. So again, I can use the same height, right, that I did for when I was looking here, which was 0.003. The span was 40 years, right? So 40 years times 0.003. That's going to give me my rectangle area, which will be about 0.12. And then the area above, I'm going to do 1/2 base times height. So to get this area, we said my base is going from 40 to 80. So that's 40 years. And then my height can be found by looking at the difference between this 0.015 and the 0.003 that I used, which is going to give me 0.012. So when I do 1/2 base times height, I get 0.24. So I have to add this 0.24 and this 0.12 to the other area that I had, which I already know adds up to 0.59. So when I add those three things together, I do 0.59 plus 0.24 plus 0.12. That's going to give me 0.95. So that's another approximation here, which is not quite as good. And the reason is you can see this extra area that's really bumpy in my triangle here, going from 40 to 80. But they're all in the same neighborhood. So again, I could check these exactly off my table. However, I can get a good approximation if I have the density function picture or the CDF by using this accordingly. So again, if you have the density function, we're looking for the area under the curve. And if we have the cumulative distribution function, we're looking for the percentage value on the vertical axis, which tells us how much we've accumulated up to a certain point. Example 3. The distribution of the heights x in meters of trees is represented by the density function p of x. Explain the meaning of capital P of 6 equals 0.45. So here, notice our density function is little p of x, but we're asking a question about capital P of x, which means that we have found the antiderivative. So we're talking about the cumulative distribution function of this particular density function. So the value that's inside our functions is x, which we know is talking about meters. So the 6 here is talking about the heights of trees in meters. Now remember, the cumulative distribution function tells us the percentage of a characteristic that happens up until a certain point. So this 0.45 is telling us that 45% of this population have a particular characteristic. So putting these two things together, we could say something like 45% of trees in this population are 6 meters tall or less. Something like that. You can certainly reword this in a variety of ways, but the key here is that we're talking about 45% of the population, and that we're talking about that represents all of the trees that are 6 meters or less. So we have to have those two key pieces of information to describe what is happening. So here we're not actually calculating anything. We're just interpreting the information. And when we interpret information, it's really important that we get the units right. So that meters is really important. And it's also really important that we realize that we're talking about a percentage of trees, the fraction of trees that have this quality of having a height of 6 meters or less. Example 4. A solar farm is auditing the amount of solar they use in comparison to how much they sell back to the city. The data in the table below show the fraction of months that have a surplus of at most D%. So what this means is that when D is negative 10%, that they are not even generating enough to cover their own needs. So they are down 10%. When they're at 0%, they're neutral. They generate just enough solar to cover the amount they use. And then, for example, at 15%, they're generating a surplus of 15% that they can sell back to the city. So we can see here the distribution. This is the cumulative distribution function for this particular situation. So notice that the values are increasing and that they are approaching 100%. So what we need to do here is we need to use this data to answer the following two questions. So A says, find the probability that the surplus will be between 15 and 20%. So since we're talking about the accumulation here, what we need to do is we need to figure out the difference between our probabilities between 15 and 20%. So from 15 to 20%, we're going from 85 to 95, which means that our change here is approximately 10%. So the percent that I'm talking about now has to do with our CDF and not the percentage. That's the dependent variable. So the probability that I'm between them is 10% because, again, when I went from 15 to 20%, I accumulated 10%. So that's the difference between the 0.85 and the 0.95. Part B. What is the most likely amount of surplus? So when we talk about most likely, we're asking which interval, which 5% interval, has the highest fraction of months that it had that amount of surplus. So what we need to do is we need to look at this in intervals, much like we did with our age problem at the beginning. Those were 10-year intervals. Notice here that our surpluses vary by 5%. So we're going to look at these in intervals of 5%. One of the things we need to be really careful about is that our first data point is talking about what happens for the negative 10% surplus. And notice at that point, we already have a fraction of the population, which means that something was happening before that to accumulate that 4%, that 0.04. Since these are in intervals of 5%, it makes sense that our first interval would be negative 15% to negative 10%. So in this interval, we know that we've accumulated 0.04, which tells me that in 4% of the months that were measured, I had a surplus of negative 10%. So I didn't actually have any extra, and I was a little bit in deficit. Now, the next interval will be negative 10% to negative 5%. So this interval here. To figure out the fraction of the time that happens, I need to look at the difference between my fractional values. Because remember, this is a cumulative distribution function, so that 0.12 is including the 0.04. So I have to subtract that off to figure out exactly how much was between the negative 10% and the negative 5%. So that's 0.08. The next interval is negative 5% to 0%. So again, I need to look at the difference between these two numbers since they're accumulating so I can figure out exactly what happened just between negative 5 and 0. So if I subtract 0.22 minus 0.12, I get 10%. And I'm going to continue doing this down my table. So the next, I'm going to look at 0% to 5%. If I subtract my two values here, I get 0.23, or 23% of the time I'm between 0 and 5% surplus here. Then I'm going to look between 5 and 10%. And when I subtract those two values, I'm going to get 0.22. And then I have 10% to 15%. So from 10% to 15%, I subtract those two numbers, and I'm going to get 0.18, or 18%. The next category here is going to be 15% to 20%. So from 15% to 20%, if I subtract those two values, I get 10%. And then finally, last but not least, I have 20% to 25%. All right, if I subtract those two values, I get 0.04. So again, my table is increasing, it's approaching 1, but the question is, what is the most likely amount of surplus? So if I look at the different intervals to figure out exactly which fraction is the highest, I see that this is going to happen from 0 to 5%. So the most likely amount of surplus is going to be 0 to 5%, because that is the fraction that's going to be the largest. So 23% of the months that are measured have a 0 to 5% surplus, which is more than any other amount of surplus. So again, I drew a table here just to chart out this information. You certainly could just look at these differences and sort of jot notes down. I find it easier to be organized when I draw and label out my table. So when we're looking for something that's most likely to happen, we have to take our cumulative distribution function and put it back into terms of our density function to figure out what proportion is going to be the largest. Example 5. The time to conduct a routine maintenance check on a machine has a CDF, or a cumulative distribution function, which gives the fraction of maintenance checks completed in time less than or equal to t minutes. Values of capital P of t are given in the table below. So notice that time, given in minutes, is given as our top variable here, and our P of t, the fraction completed, which is our CDF, is given in the second row. Part A. What fraction of maintenance checks are completed in 15 minutes or less? So remember, this is cumulative, which means that if I want to know about 15 minutes or less, that's everything accumulated up to 15. By definition, that's what the CDF tells us. So when I look at this chart and I go to 15, I see that 0.21, or 21%, of all maintenance checks are completed in 15 minutes or less, because that number, 21%, includes everything less than and up to 15. Part B. What fraction of maintenance checks take longer than 30 minutes? So here, notice that at 30 minutes, I've accumulated 98% of all maintenance checks take less than or up to 30 minutes, which means that 2%, or the remaining that would get us up to 100%, are going to take longer than 30 minutes. So I will do 1 minus the 0.98 to find that 2%. Part C. what fraction take between 10 and 15 minutes? So now I want to know specifically one interval of time. So I know that 8% take less than 10 minutes and 21% take less than 15 minutes. So if I want to know how many take place between 10 and 15 minutes, I have to subtract these two percentages. So 21% minus 8% is going to give me that 13% have to take place between 10 and 15 minutes, because from 10 to 15, I accumulated area of 13%. Part D. In which of the given 5-minute intervals is the length of maintenance check most likely to fall? So now what I need to do is I need to take the information I have from my cumulative distribution function, and I need to rework it to go back into a density function. So I need to look at how much I'm adding in each interval to figure out what fraction of the maintenance checks fell in each interval. So notice that at time equals 0, the fraction complete is 0. So I don't have anything to the left of 0 minutes. And that doesn't make sense anyway, because time is usually reported positively. So from 0 to 5 minutes, I've accumulated 0.03 or 3% of the maintenance checks happen in less than or equal to 5 minutes. Between 5 and 10 minutes, now I'm going to have to look at the difference between the fraction completed at 10 minutes minus the fraction completed in 5 minutes. And when I subtract those, I find that 5% or 0.05 happen between 5 and 10 minutes. From 10 to 15 minutes, I will do 0.21 minus 0.08, which is 0.13 or 13%. From 15 to 20 minutes, I'm going to subtract 0.38 minus 0.21, which is 17% or 0.17. From 20 to 25 minutes, I subtract those two numbers and I get 0.42. So 42% of maintenance checks take 20 to 25 minutes to complete. From 25 to 30 minutes, I'm going from 0.80 to 0.98. If I subtract those two numbers, I get 0.18 or 18%. And then we said on answer B that there's 2% that are going to take more than 30 minutes, so 0.02. So if I look at these fractions, I see that the highest fraction, or the most likely time interval to fall, will be 20 to 25 minutes, because 42% of maintenance checks happen between 20 and 25 minutes long. So that is the highest fraction and therefore the most likely or most probable to happen. Part E. Give a rough sketch of the density function. Now, what we need to do here is we need to take our different density amounts and figure out how to graph them. So we're going to be graphing these in 5-minute intervals because that's how our data is presented. So we need to graph what's happening from time 0 to 5, 5 to 10, 10 to 15, 15 to 20, so on and so forth. And what the work we did in part D is going to be really helpful because I know that the area that I need to represent on my density function from time 0 to time 5 is 0.03. However, that doesn't mean that the height of my bar graph will go up to 0.03. Instead, I need to take that area and divide by the length of the interval to get the height. We did this in the last section a little bit. So here, from time 0 to time 5, if I take 0.03 and I divide by 5, I'm going to get 0.006. So that means that from time 0 to time 5, that the height of that block has to be 0.006 because all outcomes are equally likely in this scenario. So whether it's 0 minutes, 1 minute, 2 minute, 3 minute, 4 minute, 5 minutes, they're all equally likely. That's why we have the top of our rectangle is going to be horizontal. So let's graph this first piece and then we'll see how to add the others. So on my graph, I have my time intervals on the horizontal axis and the fraction of maintenance I get done on the vertical axis. I know my time is going to be in 5-minute chunks. So I'm going to break this up into 5-minute intervals. So the first 5 minutes, 3% of maintenance checks get done within 5 minutes. So the height of this block is 0.006. So notice on my axis I have 0.05, right? So since I have 5 hash marks here, that means that this first one is 0.01. And this is a little more than halfway between 0 and 0.01. Halfway would be 0.005. So it's a little bit higher than halfway. So right about here. So again, if I multiplied base times height, I would do 5 times 0.006, and that would give me the 0.03, or the area under the curve that represents the 3%. So if I want to get the height from 5 to 10, I again need to take the fraction that I have of 0.05 and divide by 5, and I get 0.01 from 5 to 10. That's how high it goes, because again, if I multiply 5 times 0.01, I get the area of the block should be 0.05 here. Now from 10 to 15 minutes, I have 0.13, so 13% take 10 to 15 minutes. I divide by 5 because those are all equally likely, and I get 0.026. So 0.025 is like halfway. It's a little bit higher than that. So right about here is 0.026. So 0.026 times 5 gives me the 13%. That's the area of this block, because again, I'm drawing my density function. From 15 to 20 minutes, I have 0.17 divided up by my interval of 5, my 5-minute block here, and I get 0.034. So 0.03 is here, so about halfway between here and here. If I multiply 0.034 times 5, I get my 0.17. From 20 to 25, that was my 0.42. I have to divide that over the length of the interval, which is 5, which is going to give me 0.084. So 0.084 is getting pretty close to 1. So 0.08 is going to be right around here. And then 0.084 is about halfway between that and the next tick mark, a little bit less than half. So we're going to be way up here, 0.084 between 20 and 25 minutes. And 0.084 times 5 gives me the 0.42. And then from 25 to 30, I had 0.18 divided by 5 again is going to give me 0.036. So again, that's way back down here. So 0.03 is right about here. So 0.036 is a little more than halfway. And so again, the 0.036 times 5 gives me the 18%. So to get the heights for my probability, I have to take the fraction and divide by the length of the interval. Now the length of the interval should be standardized. So here we were always dividing by 5 because we were looking at 5-minute intervals. So if we take our probability of each interval, or the fraction of time that happens, and divide by the length of the interval, we get the appropriate height to draw our density function. So if we were to try to sketch a histogram of what this picture would look like, we'd try to sort of connect the midpoints in case we ever wanted to do that. to talk about the area. But we can see here that this is a good picture representation of the information that we extracted from the cumulative distribution function in the table. So again, what the CDF is telling us is how much we've accumulated up to any point. So at 20, it would be all these areas added up, and we know that when we add them all up, we're going to get 0.38. So that is in line if we were to just simply add these up. So this first one I didn't label, but I will add this in. This is from 0 to 5 is 0.03. So if we add up everything until 20, we have 17 plus 13, which is 30, plus 0.05 plus 0.03, which is 0.38, which is what's on our original table. So the CDF is accumulating stuff over time. So our next part of this problem is to sketch the CDF. So we know that our CDF is going to be an increasing function, and it's going to increase and approach 1. So when we think about what's happening and we're thinking about how much we've accumulated at every point, it's helpful to go back to our table to look at those values. So to sketch our cumulative distribution function, we are going to be plotting the values that we get from our table, because the table tells us the vertical axis values for the percentage that we've accumulated over time. So we have at time equals 0, the fraction is 0. At time equals 5, the fraction is 0.03. So that's less than 0.1, so that's still pretty low. That's way down here. At time 10, we have 0.08, so we're getting closer to that 0.1 value. At time equals 15, we have 0.21, so 0.21 is roughly here. At time equals 20, we have 0.38, so that's pretty close to 0.4, so that's right about here. At time equals 25, we jump all the way up to 0.80, which is quite a jump, so that's here. And then at 30, we're up to 98%, so up here. So we can see the path of our CDF, and it's not perfect, but we want to connect what's happening as we approach 1. So we have an increasing function that's approaching 1. We can see that it's steepest between 20 and 25. Now that's interesting because we found that the most likely maintenance time would be between 20 and 25 minutes because that had the highest fraction of maintenance completed during that time interval. It turns out that that's also where the derivative of the cumulative distribution function is the steepest. So that will always be true. If you look at a cumulative distribution function, which is increasing and approaching 1, the place that has the largest derivative or the steepest slope is the most likely outcome. So now we have a sense of how to find different fractions from a CDF, how to go back and plot the density function and talk about things related to that, and then how to graph our CDF based on the table and information we were given.